Mass and Energy Balance for Biosystem. Module 6, Conservation of Mass. Segment 3, System with Chemical Reactions. Ismi Lili from School of Life Sciences and Technology, Institute Teknologi Bandung. In the previous segment, we already discussed about the system with multi-component mixtures, system with multiple units, and now in this segment we will discuss about the system with chemical reaction. Chemical reactions are present in many biological systems. And before that, concepts such as stoichiometry, fractional conversion, and reaction rate must be mastered. What is stoichiometry? Stoichiometry is the theory of how specific chemical species are proportioned in a chemical reaction and is based on the conservation of elemental mass. The stoichiometric equation of a chemical reaction is a statement that the relative number of molecules or mole of reactant and product that participate in the reaction. And an example of a such stoichiometric equation is the conversion of glucose into ethanol and carbon dioxide during the fermentation. And the stoichiometric equation is shown below. For a stoichiometric equation to be valid, it must be balanced to meet restriction of the conservation of elemental mass. And a chemical equation is balanced when the number of atoms of each atomic species is the same on both sides of the equation. And for the example below, we can see that the both sides of the equation have 12 hydrogen atoms, 6 carbon atoms, and 6 oxygen atoms, which indicate the equation is balanced. In the system with chemical reaction, the generation and consumption terms are non-zero in the accounting equation describing mass and moles of specific chemical species, since chemical species can be transformed during a reaction. And in the general, a stoichiometric reaction equation can be seen in this slide, where A, B, C, D, P, Q, and R are the stoichiometric coefficients, and for the A caps lock, A, B, C, D, P, Q, and R are the chemical compound. Stoichiometric coefficients are numbers that precede the chemical species in a reaction that ensure the reaction is balanced. And for solving the stoichiometric coefficient, we can follow the system such as for the first time, we index the compound corresponding each reactant to A, B, C, and so on, and each product to P, Q, R, and so on. And then we index the element present in the reaction and we can give the number as 1, 2, 3, and so on. And for each element, the number of atoms in each compound can be written as the KIG, where I is the element number index and J is the compound index. And then we can construct a balanced equation using the stoichiometric coefficient. We can label A, B, C, D, P, Q, R, and so on for each element I. And we can see in this slide. And then for the last, we can solve the equation for the unknown stoichiometric coefficient. When balancing chemical reaction and using the conservation of mass equation, coefficients associated with compound consumed in the reaction are negative in sign, and the coefficients associated with compound generated are positive in sign. We have to note that to solve for n stoichiometric coefficient, there must be n element equation. For the fermentation reaction, such as the glucose is converted to ethanol and carbon dioxide, the compounds are glucose, ethanol, and carbon dioxide. And for the compound are indexed such as for glucose is A, ethanol is P, and carbon dioxide is Q. And the element carbon, hydrogen, and oxygen are indexed as 1, 2, and 3 respectively. And for example, we can look at the carbon. For the carbon, the equation element, the balance element equation for carbon is min AK1A plus PK1P plus K1Q is equal to 0. And for the A, we can write as 1, and K1A is 6, and for P is 2, and K1P is 2, and for Q is 2, and K1Q is 1. And in some cases, such as aerobic biochemical reaction that produce organic products such as biomass, frequently involve the consumption of oxygen and the release of carbon dioxide. The ratio of the amount of carbon dioxide released or emitted by a system to the amount of oxygen consumed during a given period of time is defined as the respiratory quotient, or RQ, which is an experimental term commonly gathered when operating a bioreactor. And RQ can be written as the mole of carbon dioxide is divided by mole of oxygen. And in situation where the number of element balance equation is not sufficient to solve for the number of unknown stoichiometric coefficient, the RQ might be added as an additional equation to facilitate a solution. Using reaction rates in the counting equation. When approaching a problem involving a chemical reaction, the reaction and balance equation must be written out, and stoichiometric balances and reaction rates must always be worked in unit of moles or molecules. If reactions are fed to a system in stoichiometric proportion and the reaction proceeds to completion, then all of the reactants are consumed. But in reality, both of these conditions rarely occur. And if the reactants are present in stoichiometric proportions, the molar ratio of the reactants are equivalent to the ratio of the stoichiometric coefficient. But however, one compound is limiting reactant and the others are present in excess. A limiting reactant is a compound that is present in less than its stoichiometric proportion. Excess reactants are compounds present in greater than their stoichiometric proportion. Note that just because a compound is the limiting reactant, it doesn't mean that compound is completely consumed in the reaction. One common mistake is to assume that a limiting reactant is completely consumed, but in reality this is rarely the case. In the case where the limiting reactant is completely consumed, the product and all excess reactants are present after the reaction. But depending on the extent of the reaction, the quantities of reactants are present in different amounts. And in the system with chemical reaction, commonly we know the reaction rate. The reaction rate characterizes the extent to which chemical reaction proceeds, and it is expressed in moles or moles per time. The reaction rate is a constant for a stoichiometric equation, and it is not tied to a specific species and or compound in reacting system. Within a system, a particular compound is either consumed or generated, and the generation and consumption terms are lumped together as the term sigma SR, where sigma S is the stoichiometric coefficient and R is the reaction rate. Because the reaction process must be analyzed on a molar basis, the overall rate of extensive property psi dot is replaced with the molar flow rate or N dot. And for one inlet and one outlet in a steady state, the reacting system of the reaction rate can be written for a compound S, such as shown in the slide, and for multiple inlets and outlets in a simultaneous reaction, we can use the equation like shown in the slide, where n is the index for the chemical reaction. R can be calculated using different species or compounds. However, for a particular chemical reaction in a system, R is constant, and by rearranging the previous equation, the reaction rate can be calculated as the molar flow rate input from the compound S minus the molar flow rate output from compound S is divided by minus stoichiometric coefficient of compound S. And for the fractional conversion, we can calculate as the molar flow rate input from compound S minus molar flow rate output from compound S is divided by molar flow rate input of compound S. And the fractional conversion value should be higher for the limiting reactant than for the excited reactants. So the reaction rate can be written as the molar flow rate of input from the compound S multiplied by fractional conversion and is divided by the minus stoichiometric coefficient of compound S. And the limiting reactant is mathematically defined as the minimum of the molar flow rate of input of compound S is divided by minus stoichiometric coefficient of compound S. And that's all for the segment 3 in the module 6. For the next segment, we will discuss about dynamic system. Until then, I'm Lily from Institute Technology Bandung.